So whenever you see a function inside of another function, whenever you see a function inside of another function, there's a possibility that you can use integration by substitution. But sometimes, okay, so now I notice, hey, there's a 4x squared plus 1 inside of e. But what's the derivative of 4x squared plus 1? It's 8x. Usually with substitution, it works out perfectly if the 8x appears. But I don't have an 8x. I have an x, but not an 8x. And it's actually okay if the derivative appears, but the number is wrong. So like, this one has a 1x. The derivative of the inside function, 4x squared plus 1, is an 8x. We will still be able to use substitution, but it'll be a little bit more work. So first of all, we let u equal the inside function. Then the derivative would be 8x dx. But in our equation, we just have an x. So I divide both sides by 8. To get the x dx. Now I can rewrite. What do I have? Instead of the x and the dx, maybe I'll pick up my highlighter here, highlight a few things. Here's u in yellow. There's the x dx in green. So I can rewrite this. The only thing I didn't highlight was the e, so the e would still be there. And then instead of the 4x squared plus 1, I write u. And instead of the x dx, I'm going to write du divided by 8. Now that du divided by 8, if you want, you can write that as a 1/8. And you could choose to write that 1/8 either inside the integral, or we have a property that says you're allowed to bring out a constant multiplier outside as well. This integral is easy. The integral of e to the u is e to the u plus c. So now we can substitute back in. The 4x squared plus 1. So initially, we said that we could use substitution if you saw a function inside of another function and also saw its derivative. And now we've adapted that a little bit to saying if you see a function inside of another function, so the yellow 4x squared plus 1 is inside of another function, and its derivative in any general form is there. Like the derivative of a parabola is a line. The derivative of 4x squared is 8x, which is a line. It doesn't matter that coefficient in front. We're going to be able to algebraically manipulate that out of there. Same thing in this one. Okay? I notice that a 5 minus 2x to the 4 is inside a square root. So I have an inside function. The derivative of that inside function would be some sort of x cubed graph. And I have an extra x cubed in this equation, even though the coefficient may not match. So I start off by saying, let u equal that inside function. Then the derivative du dx will be negative 8x cubed So I can divide both sides by -8. So if I do some color coding, this was my inside function. The x cubed and the dx, those are things that I can now substitute out. What would I be left with? The integral. Wow. The integral of, well, the x and the dx are going to go away. They're going to get replaced with the du. So I'm going to be left with a 1 on top because everything's gone away. On the bottom, I'm still going to have that square root sign. And I can replace that with u. The dx and the x will get replaced with du over -8. This isn't in a form that I can integrate. So I'm going to change the u to a -1/2. Now that -8 that I'm dividing, I'm going to put that out in front as a -1/8. And now I can integrate. What is our rule for power rule? Add 1 to the exponent. So I'm still going to have this 1 over -8. Add 1 to the exponent would be 1/2. Then I have to also divide by 1/2 plus c. -8 times 1/2 is -4. Instead of u, I can substitute back the 5 minus 2x to the 4. Plus c. And I think these are the ones that are the best examples of why we use substitution. Often, some of the ones earlier on, you probably could do in your head by just undoing them. But when enough numbers are changed and you're dealing with fractions, it's hard to keep all of those numbers in your head. The substitution works really nice. Again, what's the key to knowing that you're going to use substitution? You have to look for a function inside, and its derivative has to be present. Some form of its derivative. If that's the case, then you're going to be able to do integration by substitution. The good thing about the IB is this is the hardest kind of integration we have to do. We don't have to do integration by parts. We're going to do that in the advanced math class, but not in this one. So, when you have a hard one, your main strategy that you have to use is substitution. If substitution doesn't work, then you're going to have to see, is there a way that I can manipulate it in a different way? And the last question we're going to do here, they give us the derivative. 8x over 4x squared plus 1. We need to find f of x, given that f of 0 is 4. We have no integration rule for quotient rule or product rule. So the fact that this is a quotient doesn't make us have any special integration rule. We would have to either change this into a form that we could do, or notice that there's a function inside that we could use substitution. Do you notice that? I like to use yellow first. Technically that, you could think of it as inside of an exponent of -1. So if it's on the bottom of your fraction, you can think of it as an inside function. And if we let u equal 4x squared plus 1, then the derivative matches up perfectly. f of x will equal the integral of 8x over 4x squared plus 1, because that's our derivative, dx. Substituting back, we would have the integral of 1 over u du. And this becomes the natural log of u plus c, or the natural log of So now we have an equation for f of x. Is that the right point? Yes. They tell us that it goes through the point 0, 4. So we've got an equation for f of x, but there's still a plus c. If we want to solve for c, we can plug in the point. We know that when x is 0, y is 4. And we have to do some mental math with natural logarithms. Do you remember what natural log of 1 is? Do you remember what logarithms are? Logarithms are solving for exponents. The base that you don't see here, imagine there's a little e, right? That's the base of a natural log. Logarithms solve for exponents. So you're asking e to what exponent is equal to 1? Right? If something's equal to 1, then the exponent had to be 0. So all of that thinking just to figure out that c is equal to 4. We can now write out that f of x